very much, Harada. Thanks for the introduction, and good morning, everyone. It's an honor to present my research during the PhD period, and the title will be Robotic Beam Picking for Entangled Objects. And here is how this talk will be structured. We will begin with the background, the motivation, and prior work, and then I will introduce 4 projects of my research, and then I will proceed to conclusions and future work ideas. To automate the production process, manufacturing has imported industrial robots to replace human from tedious and repeatable tasks. And as one of these tasks, robotic beam picking refers to picking up objects individually from a bin where parts are randomly placed. And this is a very crucial task since it can replace a large amount of parts feeders, and it can also handle various object shapes and sizes. And robotic beam picking has been researched for decades, and here is the 2 questions we always want to ask. First is where to grasp. So the goal is to find a grasp post or the location of the object. And the second is how to grasp. How can we plan the motion and control the robot to do that? Let's first take a look at analytic approach, which formulate the problem under a set of rigid criteria. And these analytic approaches have been successfully imported to production process, and such as a task for post estimation or grasp planning. And also another approach leverages large scales of data and try to solve the remaining problems in beam picking, such as learning more robust grasp quality metrics or grasping challenging objects. Let's take a look at the various beam picking scenes. So the schools have very simple shapes, so the robot can grasp it and lift it. But for the U-boat, the robot is grasping and lifting the entangled multiple objects. And for the deformable cables, the situation becomes even worse due to the complex entanglement phenomena and its length. So these feeder cases motivate the goal of my research to overcome the challenges for beam picking using entangled prone rigid and deformable objects. And therefore, if you want to pick cluttered, complex properties and entangled objects without any models, what exactly are the challenges? First, the objects in clutter have heavy occlusions, and they always interact with the physical world, and there existing a lot of environmental uncertainties. And these objects have challenging geometries with self-occlusions, and especially for the deformable objects. They are very complex, and they have multiple materials, and it is difficult for constructing 3D models. And then this object easily get entangled in the bin. So we have to handle these rich physical interactions, and also we have to develop the representations for the entanglement, and we have to plan skillful motion. And finally, we should done all of this without any object model. To address the mentioned challenges, there is 2 strategies we need. First is that the robot should first consider not to grasp the entangled object. And several research address these issues by learning to classify or use the object models to match with the scene to search the object. And another strategy is ability of disentangling. And some prior works using the object models to plan this kind of motion, or some works even can untangle a long cable. So what we want to do in this thesis is to realize the following capabilities which the related work do not have, such as obtaining visual presentations for entanglement, or let the robot flexibly select its actions. And we also want to craft more general or effective disentangling motion primitives to handle both the entanglement and deformation issues. And therefore, to achieve the goal of picking entangled objects, my research aims at absorbing these 2 strategies together for avoiding entanglement and disentangling. And furthermore, my research also combines the advantages of analytic approach and learning approach to crafting more dexterous and robust and accurate and unified beam picking policies. And here is the outline of my research. So the object range from rigid to deformable. And my first research detects the grasp pose by avoiding the entanglement for rigid objects. And my second research aims at improve the performance of picking rigid objects, but with the ability of both avoiding entanglement and disentangling. And then we move to solve a more complicated task, which is picking deformable objects. And this research first tackles a problem of picking wire harnesses by estimating several disentangling actions. And our final research enhanced the performance of the task of picking wire harnesses by bringing more effective disentangling motion primitives. And therefore, 4 of my research thoroughly address the problem within different task complexity. And let's move on to my first research that used an analytic approach to pick rigid objects. So for the depth image contains several objects here, and we can observe that the green region have isolated objects which can be grasped, but the red regions has entangled objects which should be avoided. So the goal is to obtain such a feature map which can visually represent the entangled regions. And here we first propose a topology coordinate which have 3 attributes to quantify the entanglement. And then we use a sliding window function to combine the values in topology coordinate for each region. And finally, we detect the graph poses from the blue regions as best as we can, because the possibilities here of entanglement are very low. And specifically, topology coordinates contains 3 scalar attributes. It's right, density, and center. So the higher the right is, the more the objects are intertwined together. And the higher the density is, a group of objects are concentrated more. So the center only indicates the location of entanglement. And we calculate these 3 values by first using a depth image to obtain the edge segment and compute the causality integral between the 2 edge segments and obtain a final matrix T. And the causality linking integral GLI refers to how much the 2 line segments are twisted together. It's a numeric metric. And finally, we can compute each attribute in topology coordinate using this metric T. We can compute ready by the average of T, center by the center of mass in T, and the density by the distribution of the higher pixel in T. And entanglement, this shows the entanglement map by our policy, and the experimental result also shows our method exceeds the previous work in success rates. And here's the contributions and the related publications of my research. And next, my second research extends the first one by adding disentangling strategies and learn policy to achieve a better performance. And therefore, we can address the problem of picking up isolated objects. But what if all objects in the bin are entangled together? And this work tackled this problem by the following 3 things. First, we train a network picnet. It is trained to let the robot select if it should pick isolated objects or disentangle the entangled objects by predicting pixel-wise action performance map. And then we set a buffer bin in the middle of the workspace to let the robot drop the entangled object as a disentangling strategy. And finally, we train PONET to inform the polling directions and positions as another disentangling strategy. So we propose 2 disentangling strategies in this work. Specifically, here is a complete workflows. First, we examine if the main bin contains entangled objects or not using picnet. So if the isolated object exists, the robot should grasp it and directly transport it to the go bin. Otherwise, it will transport and drop the entangled objects to the buffer bin to reduce the degrees of entanglement. And then we examine the buffer bin using picnet again. So if the objects are singulated after dropping, the robot will directly pick up the isolated objects and transport to the go bin. And if it's not, which is the most complex scenario, we will apply PONET to let the robot pulling the object out of the entanglement and finally transport it to the go bin to finish one picking attempt. So here is a complete workflow of our method. And here are some details of the trained networks. So the picnet can produce 2 heat maps that respectively indicate the pixel-wise possibilities of two actions, picking the isolated objects or separating the entangled objects. And among these two maps, we select the map with the largest pixel value. So in this case, the optimal action will be picking. So let's see another case, but this time, the second map, the submap, has the largest values. So the robot will execute the dropping action. And PoleNet can infer the position and the direction of the polling simultaneously by predicting a heat map called a pole map. So each pixel located in this map represents the successibility of polling to the right in the image. And we're encoding the polling directions by rotating the input image for 8 directions. The PoleNet predicts the pole map for each rotated image and reasoning about the pixel-wise possibilities of polling to the right in the image. And then we select the highest value among the 8 pole maps as the direction of the polling and also the position of the polling. So the data collection is all done in the physics simulation under self-supervision and use an analytic supervisor. Our analytic supervisor contains 3 functions. First, given the full state of the objects, we vertically project them and skeleton them to obtain such a graph. And all crossings and intersections here are between the 2 skeletons are labeled using positive or negative based on if the crossings above or under. And we can see the isolated objects in pink. It has only positive labels or without any labels. But the entangled objects in blue, it has both positive labels and negative labels. And next, our algorithm can also plan polling actions in position and direction for the tangled objects, such as in this thing. So for the direction, we can obtain the projections from other viewpoints instead of the vertical projection. And the correct polling direction can be determined with the target objects has only positive labels. So the polling directions is selected using these projection angles, and the polling position is a collision-free grasp point. And next, finally, our supervisor can also determine the graph sequences. As the video shows, we can efficiently collect data by first picking up the isolated parts and then polling the entangled objects. And here's also the data set for PicNet and PoleNet, and also the number of images, and we use in total 6 object models to collect this data. And this experimental video shows how a robot empty a bin filled with U-bolts using our policy. So PicNet is used to predict the pick map and set map shown in the left bottom. And the robot select the action which has the highest pixel value. So in this time, set map has a large pixel value, so the robot performs the drop action. So after that, we use PicNet again to predict each pick map and set map to, as we can see, the robot will select the pick map value and perform the picking actions continuously. And at this time, we can see after dropping, the entangled objects cannot be singulated in the buffering. So we apply the PoleNet to predict pole maps and plan polling actions for the robot. And the robot's wiggles is raised during polling to entangle the objects. And also the experimental results shows our policy outperformed the prior work and baselines in all 4 metrics: the success rate, the completion rate, and the action efficiency, and the PPH pickings per hour. And here are also some videos shows our policy can be generalized to the novel objects like the bottom row shows, even if for non-planned objects like this one. And here's the contributions and the related publications of this work. And after we discuss the bin picking solutions for rigid objects, we'll move to more challenging tasks, picking deformable objects. So the target will be wire harnesses. They have complex geometries with bundles of deformable cables and rigid connectors. They are very important in assembly production, but it's also very difficult to automate. So the challenges will be, they're easily form entangled clutter in the bin, and also 3D modeling or simulated training is difficult due to their deformable natures and complex structures. They are also too long to manipulate in the standard bin picking working zone. And this work tackles the beam picking task using wire harnesses by two ingredients. First, instead of lifting in the vertical direction, the robot separates the entangled objects by a horizontal movement, following a circle-like trajectory. Second, we leverage the active learning to train an efficient policy using real-world data. And our policy can prioritize its grasping the isolated objects and then select the less entanglement level actions to execute. And we propose two disentangle motion primitives. Helix motion can separate the object softly from a side angle, and spinning motion can quickly destroy the entangled objects. And we also plan six discrete actions using the combination of the mentioned two motion primitives and to evaluate their performance. And in order to reduce the search cost during exploration, we also assume a linear relationship between the actions and their success rate, and also their execution times. And we use this linear relationship to predefine the action parameters of each 6 actions, such as the trajectories of the helix motion or if the spinning motion is needed. And we also assign integers 0 to 6 as action complexity, which also linearly scale with the success rates. So here is how our policy works. So given a depth image of the captured objects, first, the model-free grasp detection module samples a set of collision-free grasp candidates. And then, action success prediction module ASP.NET takes action candidates, the grasp candidates, and the depth image as input, and evaluates the success possibilities of each action and grasp pair. And finally, action grasp selection module ranks this grasp action pair and outputs the best grasp and the best action. So for training the ASP.NET, since the wire harnesses are difficult for modeling or simulated training, we use the real-world dataset to train ASP.NET. So to reduce the cost of human intervention during the collection, we first execute each action in the real world to see if the robot can successfully isolate a single one or not. So finally, our dataset looks like this. It is labeled with a depth image, a grasp point, and then action complexity and a success failure metric. So under this data collection manner, what if the labeled action is not best, is not optimal? So we can leverage active learning to adjust the action complexity labeled in this sample. So what kind of label should be adjusted? For example, the action complexity of 5 in the left figure can successfully solve this problem, but we prefer action complexity lower than 5, which can save a lot of time. And another examples will be we prefer action complexity higher than 5 to solve these failure cases. We should adjust these two kinds of labels. And here's how we do it. Generally, we manually select several samples as training data to train ASP.NET, and use the trained ASP.NET to predict the remaining samples, and query and add samples to fine-tune the ASP repeatedly. And here's the most important module, the active query selection. It continuously adds logical samples to training data. And what kind of data should be added? For example, when the complexity of the predicted action AP is lower than the labeled 1A in the successful sample, or the complexity of AP is larger in the failure sample. And finally, at this point, we've obtained a set of grasp candidates, action candidates, and their scores. So our policy then evaluates all action grasp pair and selects the one with the minimal action complexity, and to ensure successful picking. Finally, we compare our policy with the baseline. Our policy can significantly increase the average success rates and the pickings per hour. Also shows the picking efficiency in our policy. And we also add a single recovery module using force feedback. So during the transporting object to the goal beam, if the force sensor amount at the wrist of the object detect a sudden increase, it go back and release the grasped object and start a new picking all over again. So this result also shows a recovery module can further improve its success rates. And we also test our policy on a novel type of wire harnesses. It is different in length, but it has similar components. A policy can select a relatively simple action complexity for this object and And for the longest objects in this column, we can see our policy can predict it requires more complex actions, but the current motion primitives might not be suitable for this kind of objects. And here is the contributions and the publications and the patent of this work. And finally, I will move to my final project. It still focuses on wire harness picking, but using a hybrid method with more effective disentangling actions. And first, let me talk about the limitation and failure cases of my last open loop policies. First, the circling motion primitives may not be very sufficient for complex things. And also the failure cases of handling length and the poor vision predictions also be the problem. And to address all the problems, we propose to use dynamic manipulation, bimanual manipulation, and haptic feedback to solve this problem. And we use dynamic and bimanual manipulation to disentangle the objects. And we close the loop of the system using haptic feedback and online parameter tuning. And here is how our policy works. Specifically, after detecting the grasp pose using the learned vision module from our last work, ASP.NET, the robot grasps and lifts the object while monitoring the force. So if the entanglement occurs, the robot immediately stops. And then we design a swing motion as a disentangling actions. And we also design a bimanual manipulation grasp to adjust the grasp pose on the object. And after that, the robot tries to transport the objects to the goal beam while monitoring the force. If the entanglement exists, it will go back to the beginning and start all over again. And otherwise, it is a successful peaking attempt, so we update the system parameters and execute the next peaking. So we can see here, we design several force patterns to let the robot automatically select which action to perform. And here, we'll talk about why the dynamic manipulation has advantages that the previous circular motion do not have. It has unreasonable effectiveness because of the high speed and the high acceleration. And also for long object, this motion can also expand the physical range of the big peaking task. And also the generalization is also excellent for various objects. And in this work, we formulated the swing motions using the three angles of the joint, and the angular velocity and the swing times. And here the videos show the swing motions under different action parameters and under different entanglement patterns. We can see all of them can successfully and effectively disentangle the object from the cutter. And next, we design the grasping motion to avoid the robot grasp at the very end of the object, which makes no room for the next motion. So we use the regraph motion and to adjust the object pose from the end to the middle. Here is the video shows the robot first use the torque feedback on this wrist to decide which is the correct end, and then use another arm to temporarily hold the objects and to complete the regrasping process. And we also see it can perform on the longest objects, which our prior works cannot be addressed. So basically, the motion strategies are same, and our regressive motion can successfully applied on the longest objects. And finally, we updated the system parameters and threshold at the end of the peaking attempts. And if the swing motion failed to disentangle the object, we increase the swing angles and make a stronger movement. And there are also two fourth threshold. The F fail denotes to the fourth threshold of peaking more than one object, and the F stop denotes the fourth threshold when the entanglement occurs. And this two threshold can regress and decrease to a stable value like the figure shows. And finally, the experiment video shows our entire policy and to pick in various wire harnesses by dynamic manipulation, regrasping, and real-time force feedback and online parameter tuning. And our policy can achieve a success rate of 97%. And for the objects at the right side, our prior work achieves a success rate of 0, but in our policy, we can achieve a success rate of 80%. all thanks to our regressive motion and dynamic swing motion. So here is contributions of my work and the related publications of my work. So to conclude, my PhD research has focused on beam picking using various objects which are prone to entanglement. And I proposed accurate, robust, and dexterous beam picking policies with both analytic approach and learning-based approach. And vision, haptic for perception, and skillful manipulations are introduced to this policy to address the specific cases. And for the future work, there's still challenging objects such as wire harnesses with deformable natures and multiple materials. And we can visually obtain more detailed state of the entanglement and understand how the entanglement is formed and how the knot is formed. And also, a unified perception module with multiple vision inputs or the haptic feedback will be very useful. And finally, implementing more skillful manipulation plans and flexibly selecting which motion can be performed. And also preventing the wear and tear are also very interesting topic. And thank you very much for your attention, and I'm happy to take any questions. Thank you very much.